Creating smarter, more unpredictable, and more human-like AI enemies has always been a challenge for game developers. From classic finite-state machines to complex decision trees, technological evolution has made game enemies increasingly intelligent. But this isn't true intelligence. Players who replay enough times can always predict the next move of AI enemies. Recently, NVIDIA demonstrated the world's first AI boss. Projects like Avelization's AI Residence shows the potential of LLM. Academic research has documented this shift. Wang and colleagues' survey reveals LLM's potential for decision-making in game AI. However, direct LLM integration introduces network latency, escalating API costs, and limited behavioral control. So how can indie developers use strategic capabilities of LLMs without enough resources? This video documents an exploratory study addressing that question. How can a low-cost communication pipeline between Unity and an external LLM be established for a 2D top-down shooter? And what behavioral phenomena emerge from this approach? My initial approach was the AI soldier system, letting an LLM control each enemy individually through real-time API calls. But this approach failed. Network latency made gameplay unresponsive. Even using cost-effective models like DeepSeek, costs would quickly exceed most indie game budgets. This forces me to consider, was the AI soldier system itself flawed? Drawing on design patterns, particularly Robert Nystrom's command pattern, Liu and colleagues' recent research on LLM strategic reasoning, I explored a different approach. What if the LLM served not as the soldier, but as the commander? This architectural shift became the basis of my research, separating the reasoning capabilities of the LLM from the execution of the finite state machine. The architecture splits into two layers. The first layer is strategic layer, which connects DeepSeek to Unity via API and provides it with pre-designed prompts. This enables it to understand the game, recognize its role as a commander, and know that it must issue specific tactical movement commands in JSON format to NPC soldiers every 5 seconds, rather than responding to every frame. The second layer is the execution layer, where NPC soldiers are controlled by finite state machine. Most of their basic functions remain code-driven, but their movement commands are executed based on JSON instructions sent by DeepSeek. In other words, actions like NPC soldiers targeting and shooting players are still real-time responses, but where they locate players is determined by the LLM. However, Unity itself lacks this capability. Fortunately, I found my classmate Xena to serve as my technical supporter. Through collaboration with Xena and a period of research, we developed something called the orchestrator. This is the brain of the communication pipeline. It not only connects the two components, but also handles several critical tasks. First, and most crucial, is state management. We must solve a fundamental challenge: how to enable a large language model to comprehend a 2D game world. Our solution is to abstract this 2D world into a 9-grid testing platform. This way, the LLM receives information like player is in zone 5. This simplification transforms a complex spatial reasoning problem into structured data the LLM can easily process. Second is command processing. We use a prompt builder to convert real-time data into structured instructions. These prompts are sent to DeepSeek, while structured JSON commands from DeepSeek are also received back into Unity. Third is schema validation, which ensures every JSON instruction returned by the LLM strictly adheres to our predefined format, preventing AI hallucinations from causing game crashes. So, how effective is this pipeline? Over 4 months of testing, we identified 2 key observations. First, economic viability. From June to October, after consuming approximately 1.5 million tokens and 1,167 API requests, the total cost of the entire test amounted to just 4.11 RMB. A more significant discovery was the emergence phenomenon. We observed the AI commander issuing commands during testing that we had never explicitly taught it through prompts. An example was when it issued commands like hold or surround the player when uncertain of the player's location. I realized this system wasn't merely executing instructions. It was also reasoning and making decisions. This is precisely what I've been seeking, the true unpredictability. In the end, I must be honest, this was an exploration. Our prototype isn't perfect. It lacks direct comparative analysis against traditional enemy AI system. So we can't fully quantify the specific advantages of AI commander system. This study doesn't provide a final answer, but it documents a starting point. Perhaps for indie developers, the path to truly game AI might not lie in chasing bigger, more expensive models, but in more reasonable communication architectures.